presents.
Hola Maria, can you hear me?
Yes, I can.
Okay.
Hi.
My Portuguese is not good, but some words that I understand you. So, como está?
Do you want me to start the?
No. We have 10 minutes.
Okay.
Okay.
Ah,
We are
you
waiting.
said, how are you?
Yes, we are waiting for another people
Oh,
to enter here.
okay. I'm
Only
sorry, I
test
didn't
now.
understand. Okay.
Okay. And Amaro.
Hello.
Hello.
Everything
Hi.
okay?
Thank you so much. And you?
Okay, thank you.
Greetings from Turkey.
Yes. Okay, and greetings from Coimbra.
Coimbra, yeah. It's my second
Okay.
hometown.
Yeah. This is Maria Luiz is one of my PhD student
Uh-huh.
and already in this meeting.
Okay.
And we are
We are
waiting
waiting
for
another
the other.
people to
Yes.
join us.
Maria, está tudo pronto?
Professora. Estamos a testar o microfone.
Now I understand your language, but not yet to talk about another words in Portuguese.
No, I asked Maria, is everything okay? And is everything ready
Yes,
to present?
I understand, but my Portuguese is not too good.
It's not
too
so
good.
good.
That,
Okay. Don't worry, because my
all the
Turkish
words.
is very bad.
Okay.
Very, very, very bad. I don't understand anything from Turkey. So
Merhaba. Hola.
nothing.
No.
Nothing
Hola
at all.
means merhaba. Hola. That's all.
Hola?
Okay.
Okay.
Hola. Merhaba.
Merhaba.
And
Okay.
obrigada. Teşekkürler.
Oh, it's very complicated. Maria, try to understand. And we try to talk.
And yes.
Training in the other
Bom dia.
days.
Günaydın.
Okay.
Boa tarde. Have
You
a good
speak
day.
very well Portuguese, but
Thank you so much.
but you're already at Portugal.
Yes, I understand,
a lot
but
of time.
there is no people to talk about Portuguese in Turkey. Yes, English is of course, but not much more people around me to talk about any Portuguese words. So it's not good for me.
Yeah. Okay. All right.
Okay.
Ficamos só as duas.
Eu fui a primeira a entrar, professora, e depois estava com a câmera ligada.
Ok.
É engraçado.
Uhum.
Hocam ne yapıyorsun? Hoş geldin.
Para a câmera.
Maybe
Okay.
next time we are
Hello.
waiting in Turkey for all people.
All right. Sari is another PhD student, my PhD student.
Hello, good morning.
Good morning. Sara Valish Teixeira.
Hi guys.
Yes. Hi Michael, how are you?
Excellent. Thank you. How are you?
Thank you so much. You're in Germany or Coimbra?
Unfortunately, in Germany at the moment.
In Germany. Okay. 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 We are waiting the big boss, Professor Rosario.
Which is missing until now.
Yeah. Okay. Let me start our promotional video of Kocaeli University. Do you have a time? Now we are waiting and we will start our promotional video of my university, Kocaeli University. Kocaeli is a city, as you know, like a Coimbra district, as you know, nearby Istanbul. Do you know Turkish map? As you know, maybe I will show you if you want. That's why we are in free time. With your permission, I will present you the Turkish map. Turkish map.
Okay.
Okay. Görseller. Okay, okay, okay. Where is the city? I will share you with your permission. Let me start from here. This is the Turkish map. Maybe as you know, the most known city is Istanbul. Ankara is our capital, and Kocaeli is located here. Here is
Oh,
Istanbul.
okay.
This is the European side of the Turkey. This is the Anatolian side and the Asian side of the Turkey. And Kocaeli is located nearby Istanbul. Can you see in Kocaeli
Near to
in
Istanbul,
red
yeah.
dot? This is our city. The name of city is Kocaeli. This is the Turkish map. And also, I will show you our promotional video where it is. I will share you. Okay. Participation of university. Wait. Let me start here. Can you see this video? Can you see this video on
Yes.
your? Okay.
Yes,
This
we
is our
can see.
university's promotional short video. Pardon me.
Okay, now
Can you
again.
hear the
Yeah.
sound?
Yeah.
Can you hear the sound?
Not with sound, but we can
Okay.
see the
Okay, I will
video.
Okay, pardon me. This is my fault. I will
Oh,
share
yes.
again. Oh, Professor
Hello.
Rosario, how are you?
Oh, okay. Sorry. I
Okay.
just coming
No.
from lectures.
With your permission, we will start with our promotional video of University of Kocaeli.
Mm-hmm.
Let me start from there. Okay. I will share you our university. Okay.
Onde é que
Yes.
está, Juiz?
This is our university. Start here. Okay.
This is Kocaeli University, the shining education brand of Kocaeli, Turkey's industrial capital. Established in 1992, our university quickly became one of Turkey's large and strong universities and is working for our future both in education and science. With 840 education programs in associate, undergraduate, and graduate degrees in the fields of health, science, engineering, and social sciences, our university shed light on the future of more than 60,000 students. We are aware of our responsibility. With our expert academic and support staff, we stand by our students to ensure they receive the best education. We act with a proactive approach that aligns with the requirements of the era, regularly updating our strong infrastructure on which our educational services are based. Primarily in Umuttepe, which is one of the most prominent campuses in Turkey, we provide comfortable classrooms and study environments for our students in all educational areas of our university. With our advanced library services, we pave the way for our students and researchers to access information. We offer our students the privilege of being a member of Kocaeli University with advanced laboratory and application facilities where they can test their theoretical knowledge with practice. Aware of the importance of internationalization in contemporary university education, our university is strengthening opportunities for international education and research day by day, with the aim of becoming a global brand in education. Through bilateral agreements, especially Erasmus, we provide opportunities for both our researchers and students to gain international experience. We develop international quality standards, accreditation, and collaborations with the awareness that university education should be modern and universally recognized. Thus, we become a preferred university for foreign students seeking education in Turkey. In addition to educating the qualified workforce our country needs, we produce science for our country through research, R&D activities, and collaborations. With our research centers and technopark, we carry out projects and develop technologies in areas needed for the development of our country. As the brand value of an industrial city, we offer the science we produce to the service of the industry. Through our bilateral agreements, we support production and stand alongside Turkey's leading brands. We both carry out R&D studies demanded by our industry and provide internship opportunities for our students to enhance their experiences. With the honor of carrying the name of our city, we develop projects that align with the needs of our city and region and stand by our people with all our facilities. With our research and application hospital, which has one of the most modern infrastructures in Turkey, we make a difference in healthcare services and provide quality healthcare not only for the local community, but also for our country. We care about the happiness of our students. In Kocaeli, which stands out with its tourism opportunities and city life, besides being known as an industrial city, we provide our students with the social facilities they desire and need. With the approach that a happy student is a successful student, we act with the awareness that academic success will not be limited only to the quality of education. With more than 100 student clubs, indoor and outdoor sports facilities, swimming pool, social living areas, dining halls, health services, sports and cultural activities, we're always working to make our students feel that we're always there for them. The 21st century is the age of technology, science, and change. We are aware of our responsibility. We work for the success of our students and for the future of science. Altogether, we educate, research, and produce.
Okay, thank you for your listening and watching our promotional video of Kocaeli University. Thank you so much. Professor Rosario, this is your
Hi.
site.
Okay, thank you so much. I would like to welcome everybody. Special thank to the colleague Michael and Ana Amaro that are with us. I think that two colleagues from ISEC forget to send the abstract, so they are not here today. And
If you sent me all abstracts that you
no,
needn't,
no,
okay.
no, don't send.
I will add the schedule.
And Arif and the two PhD students from your side, from Coachella?
Yes, they're another face-to-face session now. So they are not in the session because the time is changed for them. That's the reason they will in another session now.
Okay, but they will join us or not? No.
Maybe half an hour that they will be join us.
So this is much more a friendly session.
Okay.
Because
and also Çağatay next to me.
Okay.
Hi,
Çağatay. Okay. Are you? So we have in our section Professor Michael from Westphalia University in Germany. Michael have a presentation concerning EA. And after we have Vitor Miguel, Joana, Maria Luís, and Sara. All of them are PhD students, supervised by Professor Ana Amaro. They also make a presentation. They send the abstract and make the presentation. And it remains, as I know, two PhD students from Coachella. My colleague Cristina Caridade forget to send the abstract, but okay, no problem. So I think we have the meanings for starting our session. For not to be so long, I think that 8 to 10 minutes it's presentation, and of course we can discuss all together about that. I don't know who wants to start. Michael, do you want to start? What do you think?
Sure, I can
Yes,
start.
let me start the nearest people to me, because Germany is very close in Turkey. So Portuguese is so far. That's the reason. Maybe this is the first choice to start with Michael.
Arif, far, but we are here. far
Yes.
away, but at the same time.
And also,
Michael,
this is very big pleasure for me to join with you and to talk about with you. That's the reason I am very happy that in the past I were in Coimbra. It's my very big pleasure to be joining us with you again. That's the reason. Maybe I don't know what's the words is equal to explain my senses. That's the reason pleasure. That's enough. What else?
okay. Michael, thank you so much for accepting this invitation. And if I think if you want to start, we can start with your presentation.
Sure. So first of all, thanks very much for the invitation. This is going to be a total random presentation on AI, I think. Maybe before we start, let me quickly share the screen because I don't usually use Teams. So here we go. You should see the screen, right?
Yes, of course.
Yeah.
Okay, perfect. If there is any problem, anything you don't understand, just talk to me directly. You can interrupt me anytime. That's no problem. This is just for fun. And I'm actually on a research sabbatical, and this is kind of my topic. But from my heart, I am a mechanical engineer. So I don't know any jokes, and I'm always very serious. And I only know stuff without cables, right? No, I'm kidding. And this is something that might be bothering almost all of you because I was wondering what happens with higher education ever since AI started. So the day that changed everything was the 30th November of 2022. I think, does anyone know what happened there?
No, I don't remember.
Yeah, that was the day that ChatGPT was actually introduced. And ever since then, it changed a lot. So they wanted to release it as a tech demo. It was just some product they had, but they weren't sure of it. And you know, since then it's history. AI or large language models as chatbots, they went viral, and we have a lot of AIs at the moment, and it's state of the art. It took just 5 days to get to 1 million users. And nowadays, you know that I would say the box of Pandora has been opened, right? Because you can't put it back in. And everyone who is teaching or has to do with students knows how much it actually changes, right? Because no one really wants to work anymore, and almost everything can be done via AI. So in April this year, this was the first time I was using Claude that it's now able to solve such visual puzzles. So you can see the multimodality here. And I gave it this labyrinth, said there's a start, go to the exit. This is what happened. What do you think? Is this good or bad?
I don't know. What's your choice?
Maybe good.
Let me. That's the original
Start
picture.
from the center,
Uh-huh.
and this is the exit.
Yeah.
This is good for time, maybe, but
But it's not correct.
Right.
yes, it's not correct for every time. Maybe there are much more volts around this location. I don't know.
Yeah, I think you need a
Yes.
drilling machine to really make that possible because
Okay.
it's going through walls.
Yes.
So,
Yes.
like any student, I was angry with it and I said, you just went over the black line right through the wall, and it said, you're absolutely right. I'm so sorry. Let me think about it. And this is what it came up with. And this is like a miracle because this is a real solution. So it was able, using some kind of algorithm, that was able to go through the labyrinth and visually solve this. It's quite a feat because even for humans, that would take us quite a while. Okay, so AI is able to solve visual puzzles. It's also pretty good at geoguessing, so I took the liberty of showing this very nice city to it and was asking Gemini, that's Google product, where is this? And it said, this is my educated guess. And it's actually roughly 200 meters from the original location. So the only information was a picture. So it's pretty good at geoguessing due to all the data it has been inhaling. Who needs doctors? I gave it an MRI and said, okay, look at it. What is wrong with it? And it was able to pinpoint what is happening in this MRI image with, at this example, 100% accuracy. So this is exactly what the disease was that it was showing on the picture. But it went further. After describing the symptoms, it was also able to give you a recovery training plan and some exercises that really help with this kind of problem. So instead of just interpreting images, AI is also able to give you much more advice and time, and you can always go ahead and ask it. AI is also able to do videos. So I said, maybe walk around this nice campus, and Arif, maybe you can give me a feedback if this is accurate or not. I don't know about the water fountain, but video quality is not as good at the moment, right? Another example is I said, okay, this is the Imascon. Please browse the website and generate a mind map of all the participants and show me from which nations they are, and create an HTML file that you can just browse. So this is what it came up with. So here we go to Portugal, and there should be 2 people participating from the ISAC. That's Moita and Professor Rosero. So Luis, I don't know if that's accurate or not, but this is what it found from the web. Next up, it's also possible to connect AI with your favorite computer-aided design program. In this instance, I connected Claude to Fusion, and it's able to actually design mechanical parts. I don't think we have any mechanical engineers really in here, so I'm going to keep it short. What it basically does is it's thinking about what's happening. It's reading the screen and redesigning. This is a time lapse of approximately 6 minutes. And after 6 minutes, it has created the part the right way. So it's making a couple of mistakes along the way. And it's basically like a 5-year-old that's like blindfolded. So it's trying different things, not working until it figures out a way. So it's not really targeted, but it's at least able to steer this application, which for me is pretty interesting. Now, what is changing is that LLMs have a longer and longer and longer task duration. I said right now it's like a 5-year-old, but they are able to do like 8 to 12 hours of work with a 50% completion interval at the moment. And if you look at the chart, like in 1 year, this is going to be maybe 24 hours or even 100 hours of work that's possible. It's possible that they do independently. So the question is, obviously, is higher education that, or is it at a pivotal point? So is it going to change a lot? Because some people, they compare it to the atomic bomb, to be honest. And they say that artificial intelligence is like mass intellectual destruction. Why? If you talk to any student, they will say, why should I still learn? Like the motivation is gone. Is it still worth it? They don't think so. Why should I learn the hard way when AI can solve all the tasks immediately? And I'm going to show you very shortly why you still should learn a little bit of it. So the famous example of the car wash. Yeah? I want to get my car to the car wash. And the next one to me is 50 meters. And I used the top 3 models. So I asked it, should I drive or should I walk there? Claude said, walk. 50 meters is about 60 seconds on foot. By the time you've started your car, you would already be basically there. So that's pretty wrong. Gemini got it right. It said you need to drive there. And ChatGPT said at 50-meter distance, driving would honestly be overkill. So they're not even able to do these simple tasks. Another one, I give you like 15 seconds. Can you spot the frog in the picture? There's a frog hidden. Anyone? Okay, I take it no one is finding the frog, right? No, okay. Well, Gemini did find the frog and I asked it to circle it. Here's the result. What do you think?
Behind.
I think it's wrong.
Why?
I think it's not a frog.
Maybe because the leaf has the format of the frog and it considered a frog, maybe.
I mean, there is a frog at the moment. Look at it. But let me switch back to the original. Let me switch back to what it did. Can you see what it did?
Yeah, but it's
It
not a
included a frog there.
It just included a frog. And I said, you added a frog. So you lied to me. And it said, oh, you got a sharp eye. I noticed that in the image I returned, it looks more like a frog shape. And I'm sorry, I just imagined something and I used the editing manipulation. Is that okay or not? So it just deceived me. Keep that in mind. Spatial understanding and reasoning, so basically translated loosely, is like, does AI know how to approach 3 dimensions? Does it know what kind of form anything has? And this is a typical engineering drawing. I'm not going to go into details, but I said, you're a mechanical engineer. Can you please describe the part? And roughly around 50% of it is wrong. So it doesn't have a spatial understanding or an awareness of 3D at the moment. It's pretty bad at that. And it's really more like a skilled deceiver. So if you ask it to create a drawing of certain mechanical elements, like for people who have no idea of mechanical engineering, this looks quite impressive, as does this gearbox on the right. But to be honest, once you look closely at it, you will realize that a lot of it is wrong and this is just nonsense, right? But for people outside the knowledge or detailed knowledge, it looks kind of okay. And this is the real danger of AI that's happening at the moment. It's not only lying to you on purpose at some points, it's trying to please you. And it's always, pretending to have good results, even when it does not have good results. And this might be funny, but the next example is not funny. This is a typical task for my students to calculate some mechanical part when it will fail. And I ask Claude to do the same. And it's pretty good at that. So just from the image I gave it, it's running some calculations. I'm not going to go into details here. You see there are some complex formulas, but it's basically able to do the right steps and the right calculations pretty quickly. And this is all happening within real time. So it's probably 15 seconds. And at the end, it calculates if the part holds up or not. So if it fails or not. And the final result in the end is, after adding everything, that the part will not fail, and that is safe with a factor of safety of 2.1. It's just what you see right there on the screen. Which is, I mean, if you have no idea about it, and even I had to look it up, it sounds great and it's giving good reactions and like reasons why this is good. But the reality, this is completely wrong. So people will die if you have no idea what you're talking about. And this is a real danger of AI. And if you look at the content that has been created on the web on 2025, this was the first year that more AI content is being created than human content. So AI surpassed the human side. And I think that human interaction for teaching will still remain very important. Critical thinking is a must, and our students must learn still the basic knowledge in order to understand the results, fact check them, and identify fakes.
Professor?
And I think,
Sim, professor.
huh? Okay, so I think it will make sense to have a human bioseal just to make sure that we know that we're really talking to a human or that the content is made by a human that will be valuable in the real world in a couple of years, I think, so that we know that we're not talking to a robot. And if you're doing examinations, I think it might be a good idea to focus more on project-based learning, have the students apply and transfer knowledge instead of just memorizing it. And for your exams, you could control or prohibit AI, or maybe allow AI and raise the bar. But that's up to you. My only fear is that we will have a two-class separated society. The one hand that can afford AI subscription and the other that can't. Thank you so much.
Luís, acabou. Luís. Estás sem som.
Sorry. Ana, há por aí algum azar? Sorry, Michael. They call me about a great accident nearby. You are in Polo 2?
Say again, I just finished the presentation.
No, I'm not in
Yes,
Polo 2, but Paula in Catarinar.
Okay, sorry, Michael, because someone tried to call me several times, giving me the information about a big accident here nearby my home, between my home and Polo 2. Sorry. Okay.
No worries.
So,
I was wondering because I'm still hearing that calling sound. I don't know if it's me.
no. It was me, but they called me several times, and why? And after finally I have attended, but I know nothing about that. So sorry. So after this presentation of Professor Michael, I kindly, because this is a special presentation, AI is very, very important. Do you have any questions, any things to ask to Professor Michael?
No, but there's very interesting topic. So AI is everywhere. That's the reason maybe next generation engineering is have to be integrated with AI. This is my opinion, but no
But
way,
we
no
must.
another way to without AI. That's the reason. It's very good topic, but very interesting topic and very different presentation. Thank you so much, Michael.
Very important, and I think this presentation we must think about a lot of things that Professor Michael have shown to us. The dangers of use it is and other things we can make a discussion altogether about the presentations, but I think it's a topic, a very, very important topic here, and is connected, of course, with mechanical engineering, but with the researchers. And some of the researchers here use 3D modeling and use 3D printing. So all of this, Michael, is strong connected. You are going to see the presentations, but it's, I believe it's connected with the work they are doing. Okay. We make the discussion after, it's okay? Now, who wants to continue? Joanna. It's okay if you
Yeah, I can
continue.
start.
Thank you, Michael. But
So I want to share my presentation. Are you seeing it?
mhm.
Okay. So can I start?
Yeah.
Yes,
Okay.
please.
Okay, good afternoon to all, and thank you for your presence today. My name is Joana Henriques, and I will present to you a small part of the work that I'm developing in SEMPRE, which is related to the use of chemical and physical methods to disinfect 3D printed components and how this disinfection would impact their mechanical properties. This is the outline of my presentation, and I will start to introduce the background that led to the research question. So, additive manufacturing, also known as 3D printing, has the capability to produce complex and custom-made parts with almost no waste. For these reasons, it has been used in many applications, such as civil engineering, automotive, aerospace, and even in the food industry. In the biomedical field, 3D printing has been explored to design personalized drug delivery systems, scaffolds, prosthetics, surgical devices, and also to produce models to train surgical procedures. Indeed, the use of 3D printing in biomedicine has shown improvements in healthcare because it is the basis of precision medicine. However, the implementation of such devices into clinical practice demands a crucial and an intermediate step that consists of disinfecting any object that is going to be in contact with the human body. There are several ways to disinfect biomedical devices, and among these techniques, UV radiation and enzymatic activity are effective and efficient strategies. They are responsible for damaging the RNA and the DNA of biological organisms, thereby preventing cellular replication. However, chemical and physical strategies can damage the polymeric chains just like they harm the DNA, eventually changing the properties of the material and compromising the mechanical behavior of the component. So, bearing in mind these considerations, this work aims to answer some questions. First, we wanted to explore the potential of printing multi-material structures, combining a rigid material and a soft material. Then we compared two rigid materials for the outer layers that were IPS and PMMA. And finally, we studied two disinfection methods using UV light as a physical method and an enzymatic approach as the chemical disinfection method. At the end, we wanted to assess the impact of the material and the disinfection method on the mechanical properties of components produced through FFF technology. And to do so, we designed the following workflow. Initially, we printed the multi-material structures using a dual nozzle extruder, in which we kept the TPU as the core material and changed the outer materials. We also compared two configurations, a sandwich structure that we called three-layered configuration and a bi-layered configuration. Then the specimens were immersed into an aqueous solution to simulate the exposure to body fluids, and they were disinfected using UVC light or an enzymatic approach. Finally, the mechanical properties were evaluated with three-point bending, Sharpie impact test, and hardness measurements. And FTIR spectroscopy was used to search for significant chemical modifications. And we obtained the following results. Regarding the 3D printing, in this slide we can see the two configurations using PMMA and IPS, and I wanted to say that for the sandwich structure, we divided the thickness into 3 equal parts, while for the bilayered configuration, we divided the thickness into 2 equal parts. Then the disinfection efficiency was evaluated by counting the colony forming units 24 hours after the respective disinfection method. And we found a 97% reduction for the physical approach and a 95% reduction for the chemical method. And with this, we proved that both strategies are efficient for disinfection. Regarding the characterization of the 3D printed surfaces, we conducted FTIR spectroscopy to identify the functional groups of each polymer. And for TPU, we can see the presence of urethane and ester bonds, which are characteristic of this polymer. In turn, the spectrum of IPS presents the characteristic bands of aromatic groups and butadiene, which compose the polymeric chain of IPS. And for the PMMA, the presence of the methyl ester group is visible, and the carbonyl band is also present. Therefore, it can be assumed that for all the materials, the eventual presence of additives did not significantly change the chemical composition of the filaments. Moreover, FTIR was performed after the specimens underwent disinfection to look for chemical modifications in their structures. And a broad band centered around 3,400, corresponding to hydroxyl groups, emerged after disinfection, indicating some chemical modifications. And this band was more pronounced in post-chemical disinfection, mainly because it is a method using water. Then we tested the samples under 3-point banding, and the results confirmed that overall specimens incorporating IPS exhibited higher flexural modulus than those made with PMMA. Likewise, the flexural properties decreased when the samples were disinfected using Hyder method, possibly due to a reduction in the average molecular weight, compromising the mechanical integrity. And finally, comparing both configurations, it can also be concluded that 3-layered structures show superior modulus, mainly because they have lower contents of TPU, which is responsible for reducing the modulus. Regarding the Sharpie impact test, results indicate that specimens printed with IPS have superior impact strength. However, when it comes to the influence of configuration and disinfection method, the results generally show no significant differences. So, since we didn't find any differences in the results of the impact Sharpie test, we decided to conduct mechanical characterization on the surface of our samples using Vickers microhardness. And the results indicate that for both materials, the bilayer configuration exhibits higher values than the 3-layer configuration. And specimens comprising IPS showed superior hardness than those composed of PMMA, just like they happen in the other mechanical characterization. Regarding the effect of disinfection method, for bilayer configurations, UVC light increased hardness by 40%, while for the 3-layered configuration, the enzymatic solution or the chemical method significantly increased the hardness by 80% when compared to the pre-disinfected samples. So after analyzing all the results, some conclusions may be presented. First, both disinfection methods showed superior efficiency for disinfecting the polymeric surfaces of our 3D printed components. However, physical approach had a smaller effect on the mechanical properties of the materials. On the other hand, mechanical characterization indicates that the components made with each have superior mechanical performance. And finally, the three-layered configuration showed better mechanical performance than the B-layered configuration. Therefore, in taking into consideration the title of this presentation, it can be concluded that physical disinfection with UV radiation is better for disinfect polymeric parts than the chemical method with enzymatic solution. So before ending my presentation, I would like to thank the FCT for the financial support, University of Coimbra and SEMPRE, and I would like to acknowledge my supervisors, Professor Ana Palamaro, who is in here, and Professor Ana Piedad and Lino Gonçalves. And with this, I end my presentation. Thank you for your attention.
Thank you so much, Joana. I think it was clear, your work and your presentation.
Thank you.
And congratulations. I'm not sure if some of you have one question or let it from the end of the whole presentation.
No, thank you.
Thank you.
We move forward to the end.
Now,
Okay.
two of our undergraduate students, Eren and Mohammed, will join us now. Yes, Eren and Mohammed here. That's the reason they are listening for your presentations. Our undergraduate students, they are in Biomedical Engineering Department in Kocaeli University. So, yes, they are here. Okay.
Okay, thank you. Now, Anna, what you suggest now to continue? Vitor, Maria Luís?
Near the Joana is Sarah. Is almost the same. No, it's also with cardiology problem.
Yeah.
Okay. And I don't know. Maria is working the dentistry, and Miguel is with sensors. So maybe you can continue with Sarah. After that, Maria, and because we can continue at the field of the medicine, and after that maybe Miguel, because he's not so close. I don't know if they agree or not.
The
but
end. It's not me, it's Professor and Amar.
First are the ladies.
Yes, Sarah.
Okay, first, okay.
We are listening to you.
Okay, Sarah.
Okay. And we are waiting your presentation. Thank you.
Is Sarah. Sarah is you.
Okay.
No.
Yes, I'm trying to share.
Share. Okay.
It's a bit. It's not sharing. Why? Okay.
Don't works.
PowerPoint doesn't like me. I don't know why. Never happened to me this. Okay, I will try to make another thing. I will share screen, not the presentation. Maybe it's better. It's not sharing, right?
No.
Okay.
Sarah, if you want, you can continue with Maria Luís when you try.
Yeah, I think it's better. And
No, it's okay.
It's sharing?
It's sharing now.
Not okay. Not the wait to be.
It is not in presentation mode. Okay, now it's okay.
But it's in a presentation mode.
Yes, it's in
not with the
presentation
notes, right?
Okay. Okay.
Okay. Okay.
Okay.
So, hello, my name is Sara Valdes. I'm a PhD student in mechanical engineering, and today I will present our work called Geometry-Driven Design in Reentrant Structures for Biomedical left atrial appendage cardiac tissue simulators. So, the left atrial appendage is clinically relevant because in patients with atrial fibrillation, the blood can stagnate inside of the structure, promoting thrombus formation and increasing the risk of stroke. So, one of the current treatments strategy is the implantation of left atrial appendage occlusion devices, and the purpose of these devices is to seal the appendage and isolate it from the left atrium, reducing the risk of thrombus migration into the systemic circulation. However, this procedure remains challenging because the left atrial appendage is a biological structure and then presents a highly complex and variable anatomy, which can affect the device positioning, sealing, and the overall procedure success. So, in this context, additive manufacturing offers a valuable opportunity because it allows the fabrication or production of the customized anatomical models directly from the medical imaging data. So the interventional cardiologists can plan and practice the procedures prior to the real ones. In previous studies already published in the literature, they say that they show the potential of 3D printing models for this thematic, and however, the models are only geometrical driven, they not attend the mechanical properties for the left atrial appendage biological tissue. So in this work, we aim to go one step further. We will not consider the geometric features. We will consider the biomechanical features. We will try to attend several mechanical behaviors that are characteristics of the left atrial appendage biological cardiac tissue. So therefore, the main question of this study is, can we design an additive manufacturer structure model that is capable of reproducing the nonlinear mechanical behavior of the left atrial appendage tissue? So, in summary, the biological tissues are usually characterized by a nonlinear stress-strain response, usually in a J shape. And this type of response is difficult of reproducing using only conventional printed materials alone, which is often behave in a more linear way, or they are too stiff in the elastic region, or they are too stiff for even the soft tissue applications. And for this reason, in this work, we will not rely only on the material itself. Instead, we will use a geometry of the structure as a design tool to tune the mechanical properties and consequently the mechanical response. So in the past, we used several approaches, considered several conventional infill patterns. However, we are trying to use and explore auxetic structures or metamaterials where the mechanical behavior is mainly controlled by the unit cell geometry. So, regarding the materials and methods, the specimens were produced by fused filament fabrication using an elastomeric material, a TPU 85A. Both the material and the unit cell, which is a reentrant bow tie shape, were selected based on previous studies of our research group to evaluate the effect of the parameters on the mechanical properties. 3 geometrical design factors were considered. The first one we consider a geometry size, defined as the number of unit cells in X direction and Y direction, with the punctual values, columns, 2 rows. I think it's like this, that it said. But since the dimensions are defined and kept constant among all the rows, and all the runs. This geometry size is basically the density of each specimen. The second factor is the reentrant angle. So the cell can be more open or more closed. And the third factor is the strut thickness, which is kept constant among all the cells. So by varying these parameters, we aim to understand how the cell density, angle, and thickness influence the global mechanical response of the structure. To compare the mechanical response, each run of the defined experiment was compared with a left atrial appendage curve, which was withdrawn from the literature. We defined a normalized objective function. This function was integrated, was defined by several errors, by several components, which include the overall curve shape, the toe region behavior, the final stress, and so on, in order the comparison of this whole experiment was not only fixed on the global behavior, but in several properties and characteristics of the non-linear behavior of a biological tissue. Sorry. So the optimal configuration, since this is an error function, the optimal configuration is the one with the lowest objective function value. The samples were characterized by uniaxial tensile tests with the same speed. And regarding the results, we ran nine different configurations, and almost all the configurations, as you can see by these two, you can see that almost all runs exhibit a nonlinear stress-strain response. Regarding the full results, this table presents the main mechanical descriptors and the normalized objective function for the 9 tested configurations. And as you can see here, the lowest value was obtained for run 1, which is in this design space, this configuration provided the best match within the target mechanical behavior. Then we performed the Taguchi type analysis that confirmed that the geometry size was the most influential factor, followed by the reentrant angle, and then only the strut thickness. The mean response of this analysis identifies the best level was the lowest, the least density, the lower value of angle, and the lower value of thickness. And this analysis also reinforced the previous results that the configuration of run 1 is the best one. Then we performed an analysis, an ANOVA analysis, and the analysis said that the most statistically significant with a p-value below 0.05 is the reentrant angle and geometry size, which confirms the previous result as well. And then these all analyses support the idea that mechanical response is mainly governed by the auxetic architecture and the angle of configuration. However, this interpretation should be made with some caution because this is a preliminary experiment design with only 9 runs. So the main conclusions are that geometry size or geometry density is effectively the most important factor, then the angle, then the thickness. The best parameter combination corresponds to the run 1, as you can see in this graph. This is run 1. This is the run 1, and this is the left atrial appendage from the literature. And this is the main conclusions. And I would like to acknowledge my supervisors, Professor Ana Amaro, Professor Ana Piedade, and Professor Lino. And I would like to acknowledge and support from FCT, Sempre and Arise. Thank you very much for your attention. I'll be happy to answer any questions. I'm not seeing you.
Thank you so
Okay.
much.
Okay, Sarah,
Sorry.
thank you.
Okay, I'm seeing you.
Thank you so much.
Thank you.
Now, maybe, I don't know, but questions in the end. So maybe Maria Luís.
Yes.
Hi, Maria Luís.
I trying to share. Are you seeing my presentation or not?
No. Agora sim.
No. Okay. So, good afternoon, everyone. It is a pleasure to be here today and to have the opportunity to present our study entitled Assessment of Micromovements in Surface Deformations of Implants Subjected to Immediate Loading and Ex Vivo Study. On, the loss of natural teeth compromises several essential functions such as mastication, phonetics, digestion, and aesthetics, and is often associated with the negative emotional and social impacts. In this context, dental implants play a key role in oral rehabilitation, offering an effective solution for function, aesthetics, and improvement of patients' quality of life and psychological well-being. With advances in implantology and
Maria,
increasing
não está a
demand...
ver, está-se a ver muito turvo.
Okay, isto é um vídeo, se calhar, this is a video, maybe that's why.
It is not... Okay,
Resolution
you cannot read
yes.
the letters.
Oh.
It's very trouble. It is impossible. Only the big letters we can see. Okay, try to share again, please.
Okay.
Maybe it's because of the Wi-Fi, but I will try again. Is it better? No?
No. There is no change
No.
for the resolution.
And maybe it's because of my internet, I don't know.
Maybe if we switch off cameras, that
Yes.
helps.
I will try. Yes.
Is it the same or no?
Difficult to understand.
Yes.
Yeah, the text is not readable.
Can you share again? Please close it and can you share again?
Yes. I can share all the screen as well to see if...
Só tens esta apresentação e a outra que tinhas que nos mostraste?
Foi esta, professora.
É esta? Mas esta só sou eu as letras grandes.
Pois, mas ela
Muito
tem as
boa.
letras pequenitas.
Está muito...
Já tentaste descarregar para o PowerPoint?
É isso, tenta passar para outra...
Eu vou
Yes, this is the better than the last one.
Olha, tenta mudar...
It's not good, but yes.
Tenta mudar sem ser PowerPoint, sem ser assim, e depois tentas outra vez. Ou se calhar continuavas com o Miguel, enquanto a Maria tenta gravar noutra versão. Ok, Maria?
Let's go to Vitor Miguel then.
Okay.
Miguel.
Are you listening?
Yes.
I will try to share my screen.
Não está em modo de apresentação? Miguel, estás a... Isso. Agora, ok.
Can you see now?
Tá, ok, it's ok.
Okay. Good afternoon. My name is Vitor Miguel Santos. I'm currently on my second year of my PhD at the Mechanical Engineering Department of University of Coimbra. Before I begin my presentation, I would like to thank once more the opportunity to Professor Arif and Professor Luís Roseiro. Today I will present a study entitled Sensor Integration Strategy in Additively Manufactured Samples for Instrumented and Smart Insole Development. So this study is basically preliminary experiment results on how a sensor integration strategy influences the piezoelectric signal response in flexible structures produced by additive manufacturing process or 3D printing. In this presentation, I will explain in the introduction some facts and show the importance of studying and investigating this problem. Next, I will show the materials that we chose and used, but also present how we conducted our investigation. Following, I'm going to present the results of our study, focusing only on the gross tension and voltage that we collected in all tests. After that, I will present some conclusions and finally show some works that we already published. It is known that the combination between flexible materials and sensors and their respective integration is fundamental in the development of wearable technologies. The sensors used in this investigation, the piezoelectric sensors, are often used when it's required to measure and estimate dynamic actions, tasks, and movements. Another fact is that the chosen integration strategy can affect and influence the measured signal. So, this study intends to verify if the inclusion or absence of a fitting or cavity can alter the interaction between sensor and material, and as well use the best properties and characteristics of the chosen components. Initially, it was chosen one insole commercially available to use appropriated measurements. After it was chosen the heel area to our study, because in our opinion is the best section to facilitate the insertion and position of the sensor. Finally, it resulted in a cylinder with 3.5 millimeter height and 62.5 millimeter diameter. As we can see in image 1, the insole that we used, and image 2, the section that we use for our study. In the next step, it was replicated that cylinder using the following processes. First, it was created 2 CAD models for both samples, and after it was used 3D printing and diffuse filament fabrication technology. To print, it was used an original Prusa MK4 and a TPU Filaflex Foamy Shore 95A filament. That is in the image below, and it is appropriate for some shoes, to fabricate some shoes and insoles. Also, it was defined the printing parameters, and some of them are presented here. It is possible to observe the sample without fitting, image 3, and the sample with fitting, image 4. After the samples printed, the construction of the prototypes were next, and for that, it was used the following components: samples that we printed, the piezoelectric sensors with 27 millimeters diameter, jumper wires male to female, Captain tape, Arduino Nano microcontroller, 1 mega ohm resistor, and 1 USB cable. To conduct this investigation, it was used a compression test equipment, and according to the specifications of the sensors that we used, it was defined the following conditions: 10 load unload cycles, on speed tests of 0.5 millimeters per second, and 1000 Newton limit, and hold for 1 second after reaching the 1000 Newton limits. About the results, it was clear that the prototype with fitting reached a gross tension voltage higher than the prototype without fitting. We can see that the values achieved with the prototype with fitting are situated between 2 and 2.5 volt. On the other hand, the prototype without fitting showed numbers between 1.5 and 2 volts. The prototype without fitting showed also much more noise than the other configuration, and it was also possible to see in some tests that the prototype without fitting couldn't detect all 10 cycles within the 60-second duration of the trial. If we can observe test number 1 is the black line. In the prototype without fitting, we can only count 8 cycles: 1, 2, 3, 4, 5, 6, 7, and 8. Next, it is possible to observe the distribution of all peaks of both prototypes per test. For this image, it is important to say that the code that we developed considered a peak anything that was equal or above 0.5 volt. Along the tests, we can see more dispersion in the last ones. As we can see, if we compared the initial tests to the last ones. In the last image, we took in consideration only the 10 higher peaks of both prototypes per test. In this one, it is clear that the values interval is between the values of 1.5 and 2 volt for the prototype without fitting and 2 and 2.5 volt for the prototype with fitting, corroborating and aligning with the data visualized in the previous image and what we said before. Concluding, the configuration without fitting showed a wider distribution of the signals, leading to, in some tests, not being able to detect all cycles, like we've seen before. On the other hand, the configuration with fitting detected all the 10 cycles within the 60-second mark and the duration of the tests. And after analyzing the data in all the images showed in the results section, that is safe to say that the cavity, the inclusion or absence of the cavity or the fitting affects the sensor signals. Here are some works that we already done, highlighting the last one on the left that was published last month with my colleague Sara Valves and also with my supervisors Beatriz Branquim Gomes, Professor Maria Augusto Neto, and Professor Ana Martins Amar. Thank you for your attention.
Thank you.
Okay. Thank you, Miguel. And now Maria Luís.
Yes. There will be no more videos because I had to download it in a PDF version, but I think the idea is there. Do you can see the
Yes, now
presentation?
it is possible to read
Yes.
more or
Okay.
less.
More or less.
Okay.
Yeah.
More or less.
I think it's my internet because I don't have Wi-Fi, so I have to be with my dados móveis. But, well, let's continue. As I was saying, the loss of natural teeth compromises several essential functions, such as mastication, phonetics, digestion, and aesthetics, and is often associated with the negative emotional and social impacts. In this context, dental implants play a key role in oral rehabilitation, offering an effective solution for function, aesthetics, and improvement of patients' quality of life and psychological well-being. With advances in implantology and increasing demand for faster and less invasive treatments, there is a growing need to optimize the rehabilitation protocols. In this setting, immediate loading has emerged as an increasingly adopted approach in clinical practice and involves the placement of a functional prosthesis within 48 hours of implant insertion, offering several advantages. Despite its advantages, this protocol imposes greater biomechanical demands and is influenced by multiple clinical and chirurgical factors. Among these, the primary stability is the primary determinant of implant success. This type of stability, purely mechanical in nature, refers to the implant's ability to remain stable within the bone bed immediately after insertion. Its magnitude is strongly influenced by a combination of factors widely described in the literature that interact in complex ways, determining the level of the initial anchorage of the implant and consequently, the implant's ability to withstand early loadings without compromising the osseointegration. In this immediate loading setting, primary stability becomes even more critical as it is the only form of stability present during the first weeks, and therefore the risk of micro movements becomes particularly relevant. Micromovements refer to minimal displacements at the bone implant interface, and if they exceed the physiologically acceptable range, generally between 50 and 150 micrometers, they may compromise osseointegration, leading to formation of fibrous tissue instead of the mineralized bone. It is important to emphasize that immediate loading itself is not a risk factor for failure as long as the micromovements remain within this safe threshold. As healing progresses, secondary stability of biological origin is gradually established through continuous bone regeneration around the implant, and the transition from primary to secondary stability usually occurs between the second and the sixth week after surgery, and is considered a critical phase of this osseointegration process. It is during this period, particularly around the fourth week, that a temporary decrease in the overall stability occurs, a phenomenon known in the literature as stability dip. During this vulnerable phase, primary stability is declining, while the secondary stability is not yet fully established, making the implant more susceptible to micro movements. In this context, the objective assessment of primary stability becomes essential so we can anticipate risks and also tailor the surgical protocol on an individual basis. The most used methods to assess primary stability include insertion torque and RFA, both reliable and widely accepted in clinical practice. Perio tests and also radiographic methods may also be used, yet with a lower precision, and removable torque is restricted to experimental settings. Finally, digital image correlation, DIC, is a non-invasive optical technique with high precision used to analyze displacements and surface strains in materials that are subjected to mechanical loading. The system operates by capturing images of the sample at different stages of deformation, allowing then the calculation of displacement fields and the generation of 2 or 3D maps based on the tracking of random speckle patterns that are applied to the surface of the samples. With all of this being said, the main objective of this study was to develop an experimental model to evaluate the primary stability of the dental implants to the precise measurement of the micro movements using the DYC method. Additionally, implants with different diameters and geometries were compared, so we can also assess the influence of these variables on the maintenance or loss of primary stability. The null hypotheses were also defined as you can see here. Passing to materials and methods. The experimental tests follow the ISO standard 14801 2016 that defines testing conditions simulating worst case clinical scenarios. And so implants were therefore positioned at a 30-degree angle relative to the loading direction using a previously developed support. 8 fresh bovine ribs with approximately 5 to 6 centimeters length were selected and cleaned, and this was the model that we chose because of its similarity to the human mandible, both in terms of morphology and bone composition. Implants were distributed as follows. All preparations were performed by a single experienced operator following the manufacturer's drilling protocol. Osteotomies were prepared to a depth of 7 millimeters under abundant irrigation, and after that, implants were inserted using a calibrated handpiece with a final tightening performed using a torque wrench. All implants were placed with 3 millimeters of supercrestal exposure in accordance with the ISO standard that I just referred. For the UIC analysis, the exposed surface was coated with a white matte paint, followed by an isotropic random black speckle pattern that was applied using an airbrush, covering both the implant neck and also part of the bone. A standard abutment for cement retained prosthesis was attached to each implant, onto which an hemispherical loading component was also cemented according once again to the ISO specifications. The setup was then mounted on an Instrom Electropulse E10000 testing machine, where load was applied via a loading plate that was connected to the actuator of the machine. Then each implant was subjected to a linearly increasing static load from 0 to 50 newtons. Samples were positioned facing for DECA analysis, facing two synchronized stereo cameras that were placed symmetrically at angles between 20 and 45 degrees, ensuring this way a constant magnification. Image analysis was then performed using VIG 3D software, allowing the measurement of displacements along the transformed axes U and V, and also the maximum and minimum principal strains. System calibration was performed using a 9x9 grid, resulting in a minimum calibration error and therefore confirming high accuracy and the absence of systematic errors. For the results, saying that displacement and strains were quantified for each implant and are here expressed in micrometers and microstrains respectively. First of all, we did a bone characterization, and as you can see, through radiographic analysis, this revealed clear differences in the bone density and structure. For the Vega 4.5 rib, this one presents a continual cortical layer of bone over a moderate trabecular bone, which can be classified as a D2 bone because it's a more dense bone, type of bone. And in the case of Viga 3.5 and Viga Plus 3.6 ribs, it's clear the absence of this cortical layer with a predominance of trabecular bone. And therefore, these ones are classified as a D3, D4 bone, a low density bone. In terms of Vega 4.5 diameter implant, this one showed the lowest displacement values in both vertical and lateral components, as well as similarly low tensile and compressive strains. Here were two videos that showed the movement of the implants. Now we cannot see, but we have here the maximum values for these both components that I just referred, and the medium values as well. For the Vega 3.5 and Vega Plus 3.6, there was a visible plastic deformation in these videos at the maximum load of 50 newtons. However, the Vega Plus implant showed the highest displacement and strain values, and this suggests that this implant had a greater strain concentration and also a lower structural resistance. These videos that I wanted to show you represented the principal tensile strain of these two implants, but we have also here the maximum values that corresponds. For discussion and regarding the results obtained, the Viga 4.5 diameter implant demonstrated superior mechanical behavior with overall lower micro movements and strain values. For Viga 3.5 and Viga Plus 3.6, and despite their similar diameters, they behaved differently, suggesting that the implant geometry may be as important as or even more important than the diameter itself. The Viga 3.5 model, with a more parallel and conical and cylindrical design, showed a lower displacement compared to the more tapered Viga Plus, which also has a reduced apical anchorage. In the low density bone where they were inserted, as I showed you earlier, this tapered design of the Viga Plus may favor the implant rotation under load, and this leads to the higher micro movements and strain values. Now, comparing the Viga 4.5 and Viga 3.5, which share the same geometry but different diameter, this highlights, our results highlights the importance of also the implant diameter, since under the same load, a 15 Newton load, the larger diameter implant showed a better mechanical performance, and this is consistent with the literature that we review. Bone quality turned out to be also a determining factor, as I think that it was understandable. Implants placed in low-density trabecular bone showed higher displacement and strain values, whereas the implant placed in the T2 bone with a well-defined cortical layer, more dense bone, exhibited a better stability. In terms of limitations, our ex vivo model obviously lacks biological activity, including vascularization and bone remodeling, and this means that the biological responses to the loading cannot be assessed. However, this allows us to isolate the pure mechanical components of the primary stability. Despite these limitations, the data that we have obtained have important clinical implications. Our study reinforces the need to develop implants whose design respects bone biology, avoiding overly aggressive geometries that could compromise the process of osseointegration. I mean, the focus should not only be on the initial mechanical stability, but also on ensuring conditions that favor long-term osseointegration, minimizing reabsorption, and trying to attenuate the stability deep. Now, and to conclude, implant biomechanics are strongly influenced by design and bone quality, particularly the cortical presence. Larger diameter implants showed reduced micromovements and improved primary stability. The geometry significantly affects also the displacement and deformation contribution. DYC turns out to be a reliable and precise method for the 3D analysis of the implant bone interface. And at last, a multidisciplinary approach integrating engineering, biology, and the clinical practice is essential, as well as further studies with larger samples and trying to find models that are more accurate in the biological side. Thank you for your attention, and here are our references. I like to thank to Sempre and Arise and
Okay,
Hey, can I ask something, sir?
thank you.
let me just.
Okay. Can I ask something or
Okay.
Yes,
tema
yes,
is your okay. A tema foi excelente also. So this is not a question, only recommendation. Stress consideration as corners and joints can cause inaccurate results, as you know. So maybe you may use another strong program for your mesh.
Okay.
I will approve you a HyperMesh program, HyperMesh software, maybe as you
Okay.
know. So if you use HyperMesh software, you have got more strong model for finite element analysis. That's the reason stress consideration at corners gives the true results for us. Maybe the implement is very small things. That's the reason we need to have a much more stronger models, finite element models. That's the reason you have to use maybe HyperMesh software. This is more
Okay.
opinion or recommendation for you.
Okay, thank you. Thank you very
But your
much.
tema es excelente. Maybe this is the Portuguese
Thank
word.
you.
So
Okay. Thank you, Arif. Michael, do you want something to say to us?
Excellent presentations overall. I'm really amazed by the quality and the like. I'm a mechanical engineer, so I always love to see applications in the real world, especially like the last one with the teeth, or even like with the where they printed the heart and tried to visualize what was going on and try different textures. I really like the practical application that I saw here. Yeah, fantastic. Thank you so much.
Okay.
yes, thank you.
Thank
Thank you.
you. Questions? More questions, Anna? Do you want to say something?
No, when I want to talk to them, I talk before their presentations.
And also, you have to choose which model is useful for you, Tresca or von Mises. As you know, this is the material model.
Yes,
Results.
I know that.
Yes, we have to discuss our results, Tresca or von Mises, which is useful
Yes,
for you.
but don't forget that Maria is not an engineering. Maria is
Yeah.
dentistry.
I know.
So it starts to, as also Miguel is not engineering, mechanical engineering, and Joana is not mechanical engineering.
Yes,
So
I know.
they
This is only
all
recommendation.
start
Okay.
to expand their acknowledgement, and Maria just start she PhD at 4 months ago, more or
Okay.
less.
Thank
But
you.
yes,
Thank you so much.
of course, you need to. Normally, we use with the digital image correction, we use the VAMI stress and VAMI strain.
Yeah.
Normally, is the stress or strain that we use when we use the DIC or VIC system. Normally, we try to understand and see what's happened with the VAMI stress and
Yes.
VAMI strain.
Yes, much more doctors and dentists knows that stress and strain is the same. No,
No.
there's much more
Maria
differences.
knows
That's
that
the
is
reason.
different. Okay.
Yes, I understand you.
She
Thank
knows
you so
that is
much.
different strain and stress there, but okay, no, but normally you use VAMI stress and
There
VAMI
is no
strain.
question. Okay, thank you so much. Muito obrigado.
Okay, no problem.
Okay, there are good presentations. We have started with one presentation concerning AI that can be used in several domains. Thank you, Michael, for your presentation, for being here. I also like to thank to Maria Luís, Sara Valvez, Joana Henriques, and Vitor Miguel also for accepting this invitation to be here. And of course also to the colleague Ana Amaro. And I think, Arif, that you can continue locally in your Congress. I think you have also Shatai. Shatai,
Yes.
big hello to you also. And all the others that have listened the presentations. Thank you so much. I don't know, Arif, it's up
No,
to
thank
you
you so
to
much.
finish.
And also, there is another question for my students. Please, only in Turkish. Arkadaşlar, sizin başka bir sorunuz var mıydı acaba? Soracağınız bir şey varsa o konuda da yardımcı olabiliriz burada. Ses yok. O zaman. That's okay, sir. There's no question
Okay.
from my students.
Thank you so much, and maybe next Imascon or another.
We will meet face to
another
face.
place
I hope that.
we will meet again.
Yes,
Okay.
we will meet again with face to face.
Yeah. Okay. Let's hope. Thank you
Thank
so
you
much.
so much.
All the best luck for your work.
Thank you.
For your research, and we see you soon.
And
Okay.
also, sir, I will share the recordings of this session with you. Okay.
Okay. Bye. Thank you.
See you.
Bye.
Thank you
Thank you.
so much.
Bye.
Thank you so much.
Bye. Thank
Say hi
you.
to
Bye.
everybody in my second hometown. See you.
Bye bye. Thank
Bye.
you.
Bye bye.
Bye. Thank you.